Hi everyone, and welcome to this video and actually this course where I'm going to show you how to build an end-to-end transformer based GPT-2 model. We're going to work from this Jupyter notebook, which is actually in Google Colab, and this is the whole project. So the idea is to create a transformer based encoder only transformer based on the original GPT-2 implementation. And this code is also based on the Nano GPT from Andrei Karpathy, so I definitely would recommend visiting this repository and checking his project as well. Here, however, we're going to use an actual pre-trained tokenizer, which means that rather than breaking every word into individual characters and then training our model with those, we're actually going to take bigger chunks, just how it's done in the GPT-2 and even up to the GPT-5 models, where we have a multi-character context for building a single token. Also, Decoder only transformer is the one used for the GPT-2 models, which means that our transformer will not know what is going to happen in the future. We're going to check just the information from the context up to a single word or token, and based on what happened previously, we will try to predict the future. So by the end of this video, you will have a complete language model that you can train yourself in any text data and then use it by asking it questions and getting the appropriate answers. Obviously, to train a very large model, you will need huge data sets, meaning that you will need a lot of text. But for this video, so you are able to train your model quicker, we're going to use a test data set called Wikisend. So I took just a small portion of the data set, which is about, I would say, 100 lines of text, and this is the text that I'm going to use to train our model. The actual data set is probably about 100 megabytes and contains data from Wikipedia. I will link it in the description of that video so you can download it, pass it to the Google Colab library, and try it yourself. So obviously, when you build AI models, it is best practice to train them using GPU. If you have a Google Colab account, you can actually do that by going to the Google Colab for this project that I will pass to the course, then clicking here, change runtime type, and select T4 GPU. That will enable your model to be trained way quicker comparing to the CPU, which is of course a topic for another video, but I'll definitely advise you to do that. Now, the first thing that I'm going to show you is how to implement a tokenizer, which means how are we going to separate the data set into individual tokens and how we're going to mark these tokens. Obviously, computers understand only numbers. So ultimately what we want to do is create sort of a dictionary that is going to link each individual token to a specific number, okay? And I will show you how we can do that. So first, here you can see I'm actually going to just run this code. We need to import Torch, which is a library we're going to use for this tutorial. And also I will check if a CPU is available, right? So since I enabled CPU, you can clearly see that it is available. And then I'm going to import all the libraries needed for this course. Now, the first thing, as I said, that we're going to implement is the tokenizer. I will actually reduce the vocab size simply because our text file is way too small for extracting 50,000 tokens, right? So here is a typical tokenizer class. So in the initialization here, we're going to create a new tokenizer. So here we create a new tokenizer, which is going to be of a type byte pair encoding that we passed right here. And if there's a character that we don't know or is unknown, we're going to mark it with U and K, as you can see here. And then this line here says to the tokenizer that initially we want to break the words based on white space, and after that we're going to see the relations between the different letters and how we can combine them to form tokens. Since we import a pre-trained model, here we're specifying our trainer, which means how the model will be trained, and here we pass the vocab size, which in this case is 20,000 tokens. Here we train our dataset using the text file and the trainer. Then here in our vocab size, we will store all the important relations between the tokens. And finally, with those two functions here, we're going to encode and decode, which means how do we convert a number to token and token to number, okay? And if you don't understand this right now, I'm going to run a specific example that will help you to understand how the tokenizer works. The idea is for us to test each and every block of the GPT-2 model, so we understand how those blocks work, and after that to see what happens when we combine them. Okay, so now let's initialize our tokenizer. So clearly here we have the definition that is called BP tokenizer. And now I'm going to create a new instance of this class. I'm going to pass a text file, which actually I'll have to change its name since we're using just a really small subset of the training data. I'm going to also change here the vocab size maybe to 1000 tokens. And after that, once I initialize the tokenizer, all the characters taken from the text file are going to be broken down in the best way into 1000 tokens. Okay, then here we're going to print the vocab size, and you're going to be able to get the complete mapping between tokens and numbers by calling the vocab variable here. The last few lines in the end, I'm adding those so you can clearly see how the whole data structure of tokens mapping looks like. Okay, so let's run the BP tokenizer, and after that I will run our test code. Okay, so the code is completed, and you can see that what we have here is that in our vocabulary we have a clear mapping between tokens and numbers, as I said. For example, with 0 we will mark the unknown token, right? With 1 we will map parentheses, with 2 we map something else, and so on. If we move along, you'll see that initially we start by dividing the text into characters, right? So for example, the number 44 is going to be representing the character A, or the other way around. If we pass the character A, we should be able to encode the character A to the number 44. And that way we are able to represent all the characters as numbers when we pass them to the transformer and the GPT-2 model. So if I move along, you see now that here our tokenizer was able to capture a little bit more complicated structures, right? So we'll have a token with number 345 that is called Go, then 346 GS, right? So if I continue, you can see that we have about actually exactly 1000 tokens, and then we're going to use those tokens to train the models, and our model should be able to always predict the next token that is coming to the sequence when it knows the tokens that are before it. Okay, so that's the idea. Now the next thing we want to do after we have the tokens encoding and decoding all set, we want to create this GPT configuration class. So here we're going to initialize the size of our vocabulary, which is going to be in that case 1000, the block size, or how many samples are going to be processed at the same time, the number of layers, the number of self-attention heads, and also here we have the number of embeddings, which means each character by how many numbers into one-dimensional vector it is going to be represented. Then the dropout will define, when training the model, how many tokens will have their weights set by random to 0 when training the model. This will prevent overfitting of our model, and so on. So I'm going to run this. Obviously this line is doing nothing, just sets up our variables that we're actually going to discuss a little bit later as well. Now the next thing that is quite important is structuring our dataset. So far what we did is we created a configuration that specify the parameters we're going to use in our model, as well as we created the mapping between tokens and numbers. So now we know what number what token represents. So before training the model, we need to prepare our dataset. In PyTorch, you're having this dataset class, and if you go to the definition of dataset and data loaders, you can see that dataset stores the samples and their corresponding labels. So obviously we will create some structure, or in this case a PyTorch tensor, that will hold the data and its labels. Okay, so let's run this class here, and under it I'll write some additional code so we can actually test it. Okay, so how do we create a dataset? So firstly, I'm going to pass a text file, so P001. Okay, so here we create a new sample text, and then I'm going to create a dataset using our text dataset class by passing the sample text, which is now converted to a Python string, our tokenizer mappings, or the mappings between the tokens and their representation in numbers, and finally the block size, which here I'm going to write it as 64. Okay, once we have those, now we can actually view our data and see what the text dataset class did. Okay, so firstly, you can see that our dataset or everything that was in our text file consists of 2954 tokens. Okay, so you should make a difference between the token mapping and the tokens in the dataset. So the token mapping is what are the unique tokens and their number representation. So obviously we have 1000 unique tokens. Okay, and when we processed our text file, inside we found 2954 different instances of that tokens. For example, if we find 2 times the token A in our text, then we will say that our data set has 2 tokens of type A, right? And if you want to see the actual tokens, we can write dataset dot arrange 0 to 100. So the first 100 tokens in our set are those numbers, right? So let's actually see how they relate to our map. So you can see here that the first token that we found in our text was 107, right? So if I go up here where we have our mapping and I search for 107, okay, this is the token D. And then if you open the text file, okay, it should open here on the side, you can see that here we captured the right here. Okay, so the very first line in our text starts with the, and this is why here you can see instead of the 107. So now you start to understand that we simply convert the text that we have into those tokens using the mapping. Let's see the next one. So the next one is 68. So if I search for 68 into our mapping right here, okay, this is the token Y, and you can see that we have day, right? Okay, so our tokenizer decided that it is going to have 1 token for the and 1 token for Y. And this actually makes sense that we don't break them into characters of exact same length, right? And for example, if you go to this page tokenizer, so platform.openai.com tokenizer, you can actually see the actual tokenizer of the GPT-4 models. Okay, so for example, in their tokenizer, we have the word day as 1 token, the word R as another token, and so on. For example, the word neurotoxins, as you can see here, consists of 3 tokens, neurotoxins, right? And in our case, the word day was consisting of 2 tokens, the and the word Y, okay? So that's essentially the reason, or actually the difference between tokens and words. One word can be separated into multiple tokens, but also there is the case where one word is 1 token as well. It all depends on your tokenizer. Obviously, the GPT-4 model uses about 50,000 tokens, which means that they are going to have way more variety, and for this reason you can see complete words that are just a single token. Okay, so far we just reviewed this data parameter here, but the other question you might have is, what is this function here? So why did we need to define the getItem function? Okay, and we're actually going to test that here. So when you define the function getItem inside the class, this means what are we going to get when we want to view just 1 index of that item, right? So for example, when I write dataset.0, which means I want to get the first element of the dataset, what should be displayed? Normally, if you have a Python list, for example, a equals to 1, 2, 3, and you write A0, yeah, you guessed it right, you're going to get 1, right? Or you're going to get the first element in the list. Now you can overwrite what you're actually getting when you write something bracket 0. For example, if I have the function getItem for this particular list, and I just return self.a idx plus 1, this would mean that I would actually not return the first element, but actually I'm going to return the element at index plus 1. So A0 will become A0 plus 1, and then I will return 2, right? So what I'm trying to say here is that the getItem function here defines what you're going to return when you want to see a certain index of an array, tensor, or dataset of iterable element, right? So this is what we are going to do here, and I'll explain you in a second why we need to do that. So in the decoder only transformers, what we're trying to do is to pass some sequence of words. For example, I want to pass to a transformer they are, and then to get the next token. So I would like the transformer to predict that the next token is 1, okay? So how do we train such a model? Well, obviously, we need to have one data set that consists of the words they are, and another data set that consists of the word 1 at the same index, right? So then I can say when you pass a.0, right, which is probably going to be equal to they are, then expect to get b0, which is equal to 1, okay? So that way, if I have two separate data sets that have at the same indices, the question, which is what should be after they are, and the answer, which is 1, then I can train our model in an easier way, right? And this is what we're doing here. So when I want to get a data set 0, what I'm doing is I'm creating two tensors, right? So I create the tensor x, which is going to give me all the elements from the index until the index plus block size, and block size is 64. So all the elements in the context are 64, right? So I'm going to get 64 tokens, and this is what I'm going to keep in x. So x of 0 is going to be equivalent 64 tokens from the beginning of data set until the 64th token. Okay, so if this is the question, those 64 tokens, what is going to be the answer? Well, the answer are going to be the next 64 tokens. So then y, or the answer, is going to be I plus 1, which is going to start at the first element, right? Not actually at the second element, and it will continue until the 65th element. So that way I will know that after the first element of x, we're predicting the second element of the text. But the easiest way to understand this is obviously by plotting those. And now here you can see that we created two tensors x and y, where x consists of multiple sequences of tokens, each sequence 64 tokens, and y consists of what is it expected after those 64 tokens. So let's see how this is done here. Now dataset 0 is going to give us x and y. Okay, they are going to be built right here. So if we print those, you can see that the tokens in x are those, and for those tokens in x, we're going to expect those tokens in y. So notice this here. Now we start from 107 token and finish at 141. So then in y, we want to predict what is happening after the token 141. So obviously it comes the token 51, right? Also here in the beginning, we want to predict what is happening after the token 107, and after token 107 at the same index we'll have the token 68, which you can obviously also see from here as well. So we're just shifting our tokens with 1. And if we want to decode those into text, here's how it looks. So we start with the token d, and for the token d, we're going to predict that the next one is y, okay, which is correct. Then for the token y, we're going to predict the next one to be r, okay? And you can imagine that we're going to feed those two tensors to our AI framework, and we're going to use it to train, right? So we're going to ask the AI to predict what is the next token. It's going to predict something, then we're going to estimate the loss or how different this number is from the number representing y. Then we're going to adjust the weights inside the model and then try next time to predict y. And we're going to continuously training until we ensure that the loss or the mismatch between what the model predicted and the actual result which we have in y are the same. Now the next thing we need to talk about is the data loader. So why do we need data loader if we are perfect in our dataset? By the way, the dataset that we're having, or this dataset here, is just one very long array of tokens, right? Only when we get to the 0th element, we are actually taking portions of 64 tokens from it. But by itself, it is just one-dimensional array. And this is where it comes the data loader. So here I added a few lines where you can actually visualize the data loader. So the idea of the data loader is to simply create multiple blocks that can be analyzed at the same time. This is done so we can use multiple cores of the CPU or GPU to analyze multiple parts of the text at the same time. So for example, if the number of batches in our data loader are 180, which came out to be the case. This means that 180 individual blocks from our text are going to be analyzed, and we'll try to find the next token in those sequences at the same time. That way we obviously optimize our training. So now if I want to visualize the batches for the X and Y, now we can see a slight difference here. So you saw that in our dataset we had a window, a sliding window of 64 tokens, right? So now since we're going to analyze multiple portions of those 64 tokens at the same time, and our batch size is 16, which means that we're going to analyze 16 64 white token sequences at the same time. Now we're going to have a 2D matrix, right? So we're going to have 16 lists of 64 elements each, and we'll try to find the relations between the 16 arrays of 64 elements in X and the 16 arrays of 64 elements in Y. And if you want to visualize those, you can see the first elements of the data loader. So I print them here. So this is the first element, and this looks exactly like, actually we can see them here, and those look exactly in the same way, so exactly the same number of elements, just as we saw when we displayed the first element in our dataset, right? So here we have a sequence of 64 elements for X and 64 for Y, okay? And we have 16 groups of those tokens, right? So if I decode this as a text and actually want to display all the batches, you can see that here we're having 16 different samples from our text, right? And this is for X. For example, if I take this and I open a text file and I search it here, you can see that I found the exact sentence where those tokens are used. So here at sample 0, we have a separate token for lock, then we have another one for ated, then within is one token, the is one token, and so on. Okay, so this is one of the samples that we randomly picked from the middle of the text. Then in the next sample, we have here Colin Mount Gumier, right? And after that we have dot, and then we have the next sentence. So this is another sample. And in that way, we're going to pick 16 different samples from the text and try to predict what is coming after each character in this sample using our Y tensor. Okay, so I'm going to remove the text and let's recap what we learned so far. So far we learned how to break our text into tokens and map each of those tokens with a number, so our computer can understand those numbers. After that, we learned how to create a dataset, okay, and represent the complete text in our file as a sequence of tokens. We also learned how to extract specific blocks of those tokens and how to predict the tokens that come after that. And finally, we learned how to create a data loader, which really extends our dataset by creating multiple datasets, in our case 16 batches of 64 tokens, and try to predict the next tokens after them. And the reason for that is so our GPU can process multiple portions of our text at the same time. So now that we have our datasets all set, we can actually move on to the multi-head attention block. And obviously here we're going to work in multi-dimensional matrices, which you will see in some cases are 3D matrix to 4D matrix. But if you really want to learn how the self-attention block works and how all the weights and biases are estimated there, I would really advise you to watch this YouTube video by Josh Starmer, which is great because it really explains the transformer architecture just as if you're a kid and somebody needs to explain this complicated topic to you. So it's a 30-minute video. I would really advise you to watch it. Now, briefly, a self-attention block breaks all the tokens into our text into curious keys and values. And those curious keys and values are used to keep and estimate a specific information about the text preceding a specific token. So the idea is that we create something or some architecture that works as a memory. So when somebody tries to process a text and think about text, we need a few things. First of all, the position of the different words is obviously very important. Another important thing is the significance of every word in a sentence. Obviously, if we want to say the sentence, I like to eat pizza, clearly the word to is not as important as eat or pizza or as the word like. So we need to find a mechanism to give a higher importance to those words that are actually of significance for the meaning of the sentence. At the same time, if we are writing decoder only transformer, this means that only the words that we see before the current word that we want to produce are important. We don't want to look in the future when we try to predict the present. The only information that we want to have when we predict the present is obviously the past. So that's the whole idea behind the decoder only transformer, and you're going to see how it works when we implement this causal self-attention block. Now let's go step by step so you can understand every element from it. Now here, when we initialize our block, we're going to use our GPT configuration class that we defined earlier. And inside this class, obviously, we have all the values such as lookup size, block size, number of layers, number of heads, and so on. So we're going to use that. And that way, when we pass self.number of heads equals to config.number of heads, we'll make sure that the value used for number of heads is the value used for number of heads into our configuration. Right? So number of heads means how many transformer blocks we want in our self-attention. So you can see here from our configuration, and actually I'm going to copy this down here so we don't need to move up consistently. So you can see that the number of heads that we're using is 8. So we're going to have 8 independent query key value pair transformers. Okay. So remember where we created a number representation for each token in the text. So when we're working with transformers, we cannot simply pass a number from 0 to 1000 for each individual token. So instead of that, we do something else. We can represent each word by embedding. So for example, for the token cat, we can create a one-dimensional vector with different numbers from -1 to 1 that will represent that specific token. And then we can use that into our model. That way, we prevent ourselves from running into scaling issues because every single token is represented by an array of numbers that are within the same range. Okay. So embeddings are also showing the similarity in between words. So for example, similar words, for example, the words for animals like cat and dog, are going to have similar embeddings. Okay, so you can see that the embeddings for those two words are pretty close. And this is because they're both animals and they're both pets and so on. So we are going to put a similar meaning to those words. Although since they are not the same, still our embeddings are going to be slightly different. But the embedding, for example, for building is going to be way further from cat comparing to dog, right? So that's the idea of embedding. Now, what is the relation between the number of embeddings and the number of heads? So if we have 8 heads and 512 embeddings, this means that for each head, we will have the number of embeddings divided by the number of heads, which will be 512 divided by 8 will give us 64 embeddings per head. Okay, so every token will be represented by an array of 64 numbers, and those numbers are going to be different for every head. Okay, so each word will have a different array of 64 numbers, and each head individually will update those numbers to find interesting relations between the words in every head. And later we're going to talk about how after that we're combining those numbers so we get our final similarities between the words. Okay, so the next thing that we're initializing, by the way, pay attention that here we're in our initializing block where we simply specify what are the initial values of every variable, right? So here we simply have the number of heads, the head dimension, which is 64, and the scale, or how we're going to scale our output, for which we're going to talk about later. After that, we want to initialize the Q, K, and V, which is the query, key, and value elements for our transformer. And the length of this neural network, which is simply a linear representation, is going to be 512, because this is the number of our embeddings, by 3 multiplied by 512, which is about 1500, right? 512 multiplied by 3, okay, by 1536, okay? And this is going to be a tensor that is going to carry the information for all the query keys and values for every word. Later on, we're going to break this tensor so we can have individual values for the queries, keys, and the values, right? And those are completely random parameters, okay? And the idea is to update those parameters when we have interesting relations between the words. Then the out projections are going to be, again, a linear neural network, which is going to represent a tensor of 512 by 512 embeddings combined for all the heads. And we're going to use that to actually convert our calculated self-attention queries, keys, and values into the final result. The idea is that what it gets inside our causal self-attention is exactly the same dimension with what it gets in. So the in and the out dimensions should be exactly the same. And this is used exactly for this conversion, but we'll see how this works later in our forward loop right here. Okay, and finally we're going to initialize our dropout sets, which is going to define the percentage of our weights that are going to be initialized or actually changed to 0 by chance. That way we can prevent overfitting of our model. And overfitting means that our model is only capable to work just with the inputs and the outputs of our text file, but is not able to predict tokens of any other files, right? Or it doesn't do it with the same quality. So that's why we need our dropout sets. So those are all the initializations, and in the forward function we're going to work with those in order to find specific relations between them. I added those comments here, actually print statements, and you can see what's happening into our network. Okay. Also, to test the self-attention block, I added this demo run right here. So what are we doing? Now, firstly, we're initializing the configuration that we created earlier. Then we create the attention, so we run the self-attention and we pass the configuration. Okay, so when we run this line, the initialization block gets executed. Okay, and once we do that, we're defining some fake batch, right? So we create a batch size equal to 2, sequence length equal to 16. Well, this is going to be our time dimension, and then the embedding dimension is going to be equal to 512. And the run then will fill those spaces with numbers from a Gaussian distribution. Okay, so those numbers are obviously going to be completely random. Now, once we fill those, the idea is to create this X, and then we're going to do one forward pass, which means that with the randomly generated weights into our X matrix, we are going to try to predict our output, which is going to be at this point completely wrong because we have not yet trained our network. But this is going to be enough for us to see how our network processes the data. Okay, so what happens? Once we create output equals attention, which is our self-attention model, equals attention X, then the forward function gets executed. Okay, so firstly, we get the dimensions of X, which in our case, X is 2 by 16 by 512. And you can confirm that by this print statement here. So if I print X.shape, it's going to give me here 2 by 16 by 512. And then from the shape of X, we estimate the QKV matrix or tensor, right? So QKV approach is equal to linear number of embeddings, which in our case is 512 by 512 multiplied by 3. Okay, so this is going to be our query key value tensor, which is, as you can see, 2 by 16 by 1536. So the idea is to get 512 embeddings, and from them we're creating 3 times that with a linear representation or linear relationship between those. Now, after we do that and we have a linear representation of our embeddings, now we can break the Q, K, and V into different tensors. So to do that, you can use the split function, and what I'm saying here is I want to split the QKV, and I want to do that by C, which C in our case is 512, and I want to do that in dimension 2. And dimension 2 of the QKV is 1536. So what we're doing here is we're creating from this tensor 3 separate tensors, each of those with 512 embeddings for each. Okay, so now they have exactly equal size. And clearly, if you print the shape, you're going to see that now here the tensor for QK and V is 2, which means 2 batches. Each batch has 16 tokens in a window, and each token is represented by 512 embeddings. Okay, so now that we have those, we want to make sure that we have curious keys and values for every head. So as you can see here, we have 8 heads, right? But our current query keys and values can run only on a single head with 512 embeddings, right? So we want to change that, and we want to make sure that we can actually take embeddings for each separate head. So as we said earlier, the head dimension is equal to the embeddings divided by the number of heads, right? So in those lines here, what we're simply doing is we're saying, I want to create a new Q matrix, okay, that is going to be of a size batch, so 2 by 16 by number of heads, which is 8, by head dimension, which we found out is 64, okay? So now, because of that, the number 5, so the view function can break the matrix in any dimension, but only if the new dimension, or when you multiply the new dimensions, you get the previous one. So for example, if we want to convert the matrix 2 by 16 by 512, and we want to break the 512, so the third dimension, into 2 other dimensions, we can break that into 8 by 64, okay? So because 8 by 64 equals to 512. So what we're doing pretty much here is we're breaking the number of embeddings for the combined heads to the number of embeddings for the separate heads. So for each of the 8 heads, we're going to get now 64 embeddings, okay? And that will allow us to run all the embeddings on different heads, and consequentially to have different algorithms that look at different relations between the tokens in the text. So this is what the view function does. Now, in order to prepare the queries, the keys, and the values, and to make them suitable for other operations that PyTorch is going to do with them, we need to swap the heads and the blocks, right? So now we're going to write a dot transpose, and we're going to swap the dimension 1 with dimension 2. So 2 by 16 by 8 by 64 will become 2 by 8, so 2 batches. At each batch, we're going to have 8 heads. For each head, we'll have 16 blocks, and then in those 16 blocks, we're going to have 64 embeddings, okay? So each of those numbers into the 16 heads is going to be represented by 64 dimensional embedding. And to verify that what I'm saying is correct, now we can print Q. So you can see that we did the same thing for Q, K, and V. And if I go down here, so this is where we print the Q, you can see that Q is 2 by 8 by 16 by 64. Now the next step in our self-attention block is to get the attention scores. So an attention score can be found, and this comes from the transformer paper. It comes by multiplying the query to the key, actually to a transpose version of the key, right? So this is going to be our attention score for each token. So we can do torch.mathmul, which we use to multiply matrices, and we're going to multiply Q by the transpose of K. And here we can see that we're transposing only the last 2 dimensions, because this is only what we care about. The other 2 are the 2 batches and the 8 heads, right? So clearly we want to keep all the actions within each head in the batch, so we're not going to play with those, but what we want to play with is the features and the blocks, or the window in which we're looking when we're trying to predict the next value into our sequence. The mathmul simply performs the dot product between the 2 matrices, and after that you can see that we are multiplying every matrix by the self.scale, which also comes from the original transformer paper. And this is, if you see here, 1 divided by the square root of the head dimension. And this is done to prevent very large dot products, unstable gradients, or very picky softmax. Sometimes when you pass your numbers through a softmax function, if you don't do that, you might get too high values for some of the parameters in your softmax function. So the softmax will pretty much lean to the most possible answer and will not actually pay that much attention to the one that comes on the second place, even though it was close. Okay, so this is pretty much, I would say, a trick that allows us to stabilize the gradients and to make sure that all the values are within reasonable dimensions. So now here we can print the row attention. So the row attention would be 2 by 8 by 16 by 16, right? Just because we're getting here the the dot product of 2 by 8 by 16 by 64 and 2 by 8 by 64 by 16. Okay, so that comes from the matrix dot product. Okay, so once we estimated the attention score, the next thing that we want to do, perform the part that makes the casual self-attention casual. So here we're going to apply a mask that is going to hide the values that are happening in the future. If you remember from earlier, I mentioned that in the decoder-only transformers, we only care about what happened in the past in order to predict the present. Or we take into the consideration and we pass attention scores to all the previous tokens and take this into account when trying to predict the current one. So if we actually want to do that, we need to create a mask. So here I'm creating a mask in a 4D matrix, right? And you can see that this mask is going to affect only the last 2 dimensions of our matrix. So t is equal here to 16, right? And I'm going to create and write attention.masked fill, and I'm going to replace all the future values or all the values that are 0 with infinity. Okay, so you can see here that in our attention scores, we're masking all the future values with infinity. By the way, maybe here is a good idea to take a step back and to think a little bit on the idea behind this matrix. So you can see here, let's say, here instead of the number that represents a token, we have an embedding, right? So when we try to predict the next embedding, we only want to take into the consideration the first one, right? When we try to find the value for the next one. Then when we try to find the value for the third one, we only want the previous 2, okay? And you can see here that we're doing this in 16th score matrix, right? So we're seeing 16 scores and we're trying to predict the next one based on the context of the ones before it, right? And once we reach the 16th one, we then get to the next entry. But clearly when we are estimating the next value, we don't want to have information about the values that come after it. Okay, after that we pass the tokens through the softmax function and we set random weights to 0. So you can see that once we do that, and if you want to print the masked plus softmax attention, you see that here we're just going to have values from 0 to 1111 based on the importance of the words in the context, right? So for example, obviously here for the first word, it is the most important word because it doesn't see anything else in the context. So we found out that her softmax attention is 1.11. Now, when we have 2 words in the context, the current word is 0.61 and the previous one is 0.5. Now let's see when we have all the context filled and analyze the numbers. So when we're predicting the next value, you can see here the importance of each word. So here I can clearly see that, for example, the word disposition had way more importance for the output comparing to the word, for example, after that was equal to 0. Okay, and those weights really are giving scores for each individual word when we try to predict the output. Okay, so now once we have that, we need to find the weighted values, which is very simple. We simply are getting the dot product between the attention scores and the values, the value matrix. Okay, and this also comes from the transformer paper. So once we do that, our weighted values are becoming 2 by 8 by 16 by 64, which comes from the dot product, because when we multiply t by t to t by head dimension, we're getting a matrix with shape t by head dimension. Okay, so those will be the weighted values that are predicted based on what we have got from x, from what we pass to the forward function. So now here we have y. Okay, now so this is for each individual head, right? So this is here we're pretty much going to have the values that are predicted for each of the 8 heads, right? So 64 values are going to be predicted for 16 batches for head 1, for head 2, head 3, head 4, and so on. Now the next thing we want to do is to combine the information of all the heads together. Okay, so now we're trying to reverse engineering the process. So to do that, firstly, we're going to transpose back the Y matrix. So remember here, when we were building the curious keys and values, we did the thing the other way around, right? So we transposed the head number and the number of elements in the window, right? So now we're doing it the other way around. So we transpose that, so heads become the third dimension, okay, and after that we do view, so we change the dimensions of the matrix, so the batches stay the same, the sliding window or the block size stays the same, it's going to be 16, and now we're combining the number of heads and the head dimension. So from data that came from all the heads, we're creating just one. Okay, so once this is done, you can see that we are going to have matrix that is going to be 2 by 16 by 512. Once this is done, we just have one final step, which is to again pass through our linear layer, which, as you can see here, takes the same number of inputs and returns the same number of outputs. So why we do that? Why do we need to have another layer right here, a linear one? Well, if you think about it, when we combined the numbers from each individual head into our 512 embeddings, we actually keep in every line of those 512 embeddings individual information for each individual head. But what we actually want to do is to find also the relation between the information from each individual head. Otherwise, we're just going to keep those separated. So here we're clearly finding some linear relations between the information from each individual head, and after that we're going to finally return the scores, taking into considerations all the heads that are part of our self-attention block. So this is the reason why we pass another linear layer, and this is our out approach right here. And after we do that, we pass this through our race dropout, which is again something that is going to zero out about 10% of our attention scores randomly. Okay, so once we do that, now finally we can return the y dot, actually we return y, and you can see that here I printed y dot shape, where it is. So here is the output, and you can see that the shape of what we return is 2 by 16 by 512, which is exactly the same as what we passed to our neural network. And so once we're done, you can see the shape of the output, which is exactly the same, and then you can see the complete tensor with all the weights that we predicted for x. So next, when we move to our training, you'll see how with backpropagation we can actually improve those scores to be more relevant to the text that we're passing. So we're going to learn from the mistakes. By the way, those numbers here are going to be initially, for the first pass, completely random, because we created all the curious values and keys randomly. But with backpropagation, we're going to be able to improve those numbers and change them based on our results for y and how similar they were to the actual information that we had in our text file. Now, once we implemented the self-attention block right here, we can continue and move to the other layers that we need as part of our transformer. And the next layer I'm going to show you is the multi-layer perceptron. So as you saw from the self-attention block, the information in between the different neurons have been mixed, right? So here you can see that we created the keys, queries, and values, and we're multiplying and processing the embeddings that come to this layer while mixing them. So the idea behind the multi-layer perceptron is to process each token independently. And this is really the thinking part of the transformer. The MLP layer gives to our transformer the expressive power or the power to analyze each individual token that comes to it. And this layer, as you can see below, it's pretty simple, and it involves two linear layers, a GELU activation function, which is very similar to the residual activation function, and it's a very common nonlinear activation function that is used in the transformers. The reason we need to use the GELU activation function here is to add some non-linearity to our results. So as you can see, when we enter this layer, we enter with the number of embeddings that our model has. Then we expand this 4 times, as you can see here. So we give to the model enough space to express intermediate computations. After that, we're passing through the GELU layer right here. So actually here in the forward is where we run the layers, right? So in the init, we just define the layers, how they are going to look like. And then in the forward function, we're actually executing them. So you can see that firstly, we go through the linear layer 1. So let's say from 64 embeddings, we are going to expand this to 4 times 64. After that, we're going to pass through the activation function. And finally, we're going to size down to the initial embeddings that we had, right? So let me actually demonstrate this. We can run this layer. Sorry, I actually had to go up, so I rerun those previous layers. So here we're running our tokenizer, and then let's start the configuration, the initializing of the datasets. And then here in our cross self-attention, I actually commented out our comments so we can take them out of the way. Okay, and then let's run the MLP. Okay, so now the first thing that I want to do is here in our forward function, I'm again going to write some print statements so you can see how our matrix changes while passing through this layer. And really with the transformers and any other neural networks, we would ultimately want to combine different classes representing the self-attention, the multi-layer perceptron, and so on. And each of those classes are going to have different layers, of course. That way, it is way easier to run through the complete process and have the things organized. Okay, so this is how the shapes are going to change. And now I'm going to write a very simple command that will actually create the MLP layer. So here I write config equals to GPT configuration. Okay, then MLP equals to config.nemd. So this is going to be the number of embeddings that are going inside the layer. And then the config.dropout, which should be, I think it was 0.1. I'm going to copy again those configuration parameters here so we can easily see them. Okay, so here we create the MLP layer and we pass as an input the number of embeddings, which in our case is 512. Okay, then the dropout, as I said, is 0.1. Okay, so now we have our MLP layer, and after that I'm going to create a transformer input that we're going to pass through our forward layer. Okay, so let's do just how we did for the self-attention block. So I'll create a matrix and we're actually going to separate the dimensions, right? So B by T by C, and we're going to have 2 batches, 16 blocks, and we're going to have 512 embeddings for each. And after that, I'm going to write X is equal to torch.run B by T by C. So we're pretty much going to fill and we're going to create a 3-dimensional matrix with random elements. And then once you run, so if I do output equals to MLP X, okay, so once I do that, MLP X, the forward function will actually activate, and then we'll go through each and every layer. Okay, and here I'm gonna write final output, and we'll be able to see the shape of our output and also the complete matrix, right? So let's go through it and let's click run. Okay, so we don't see the output because I have to rerun the MLP layer again. So let's do that. And now you can see how the input gets processed through the multi-layer perceptron. So the input is 2 by 16 by 512. Okay, and this 16 that you can see here, T, the time dimension, this is pretty much showing what is the context or how long, what is the length of tokens that we analyze at the same time while trying to predict the next one. And in this case, we have 16. Then we have 2 batches, which means we analyze 2 sequences of 16 at the same time in parallel. And then each token in those 16 tokens that we analyze is represented by 512 embeddings, right? We already talked about what embeddings are, so I just wanted to clarify this before continuing. So when we enter our forward function here in the MLP, we're entering with 2 by 16 by 512, and you can see that after that in the first linear layer we obviously expand this by 4 times in the embeddings dimension, so we exit the first linear layer with 2048 embeddings, right, for each token. Then we go through the GELU activation function, which will add non-linearity, and there we don't need to specify a number of embeddings. The function is pretty straightforward. Actually, let me show you how the GELU activation function looks like. So you can see here, for example, there is a comparison between the GELU and the REU activation functions, and REU is of course way more simple, as you can see, but this line here is pretty much represented by an equation which looks like this. So the only thing that we do here is we pass each embedding through this equation and find the result, right? Okay, so after that we expect our layer to actually return exactly the same shape of matrix that it received. So we're going to size down and we're going to pass through the second linear layer right here, which is actually going to size down, right? So in the second linear layer, we expect 4 multiplied by number of embeddings, and it's going to output the same number as the number of embeddings. So it will get 2048 embeddings, and it will return 512. Okay, so you can see that after the second linear layer, we have 2 by 16 by 512 matrix, and finally we're running the dropout function, which I already explained what it is. It pretty much tries to zero out some of the embeddings, so that way we prevent from overfitting. And then we receive the final output that looks like this. Okay, so I actually printed just the first element of our output so you can see how it looks like. Okay, so this is going to be actually the first batch of elements, and it will represent 16 by 512 matrix. So then if I want to go even further, so let's say I want to print one of the 16 tokens in the sequence. So let's say let's do token 16. Actually not token 16, but the token 16. If I try to do that, actually we need to go 15, because in Python we put the numbers from 0 to 15, and those are 16 elements. You can see that here this represents one token, for example the letter A, right? And it represents it by 512 numbers. So those are our embeddings for batch 1, token 16. Okay, so I just wanted for you to visualize how we move from batch to token, and then how we see the embeddings that are representing that token for the layer. Okay, so I will again comment all of this out, so we don't need to print things when we move to the next layer. Okay, and then we can move to the transformer block. So now that we have created the self-attention and the MLP layer, we can essentially combine them in a self-attention block. So you can see here that we define one linear layer. So the LayerNorm is a very simple concept, and it's essentially a mathematical operation that normalizes the values within each token embedding vector. It ensures that every vector has a main equal to 0 and variance equal to 1, and we're going to see that in a second. So let's say in this layer, if we have a value that comes, for example, let's say for each token that has a size of 512, it will come into those numbers that are normally between -1 and 1. Then the LayerNorm will calculate the main and the variance of those 512 values. It will normalize them and will essentially scale and shift them. The purpose of that layer is to pretty much stabilize the distribution of activations. So after we pass the LayerNorm, then as you can see, we're going to go through the self-attention block. So we define it here. Then we'll have another normalization layer, and finally we're going to pass through the multi-layer perceptron, where we're going to do the actual thinking for each token. Okay, and all of this is called a single transformer block. So imagine every transformer block will have a self-attention mechanism that can have multiple heads of self-attention. It has a LayerNorm and also a multi-layer perceptron as well. And you can actually see this from the Attention is All You Need paper, where we have the transformer block specified here. Obviously, GPT is decoder only transformer, so we only care about this block right here. And you can see that we're doing exactly the things in order. So we defined the masked multi-self-attention, we defined the normalization block, and this feed forward that you can see here, this is actually how the MLP is called in this paper, right? So we have the feed forward, we have the normalization, we have now the multi-head self-attention block. And what we're doing now is we're simply combining those, just how it is done in the paper. We haven't added yet the positional encoding, and also we haven't added yet the softmax function, but we're going to do this later on. Now we only care about this self-attention block right here. So you can see that inside the paper we're essentially adding the previous values to our mass self-attention, and after that to the norm. You can see that here I actually combined all the steps together, but in the example below, which I'm going to run right now, I actually separated them. So how I broke this down. Now, firstly, you can see here, firstly we calculate the normalization, right? And we pass it through our self-attention block once we normalize the input. And then we combine this with the previous value for x. After that, we get the result and we pass it through the second LayerNorm. Then we pass it through the multi-layer perceptron and add it to the previous result. So let's see how the dimensions of the matrix change here. I'm doing the same example to test this specific block, and I'm creating a new configuration. Then we have an instance of the block, and the size of the input is going to be again 2 by 16 by 512, and this is where we run the forward function, the forward pass. So we start by block size 2 by 16 by 512. We pass through the linear layer, which returns, actually all the layers are going to return 2 by 16 by 512, because if you remember the self-attention, the idea of the self-attention is to take an input and to return the same size of an input, but simply update the embedding values and to check the relationship in between them. The MLP is actually doing the thinking for each token, so it will again take certain size of input, process it, and then return exactly the same size of input, but with the adjusted embeddings based on the thinking that each token has done by itself. And for that reason, since we designed our layers in that way, we're going to get exactly the same size of matrix everywhere. And you can see here we pass through the layers, and this is our final output. Okay, so it is again 2 by 16 by 512 three-dimensional matrix, and we have for each 2 batches, as you can see here. Each of the batches has 16 tokens, and for every token we have 512 embeddings. Okay, so now by this point, by exiting the block, we already saw what is the dependence between the different words in a sentence. And also our network is capable of realizing how important each word is, right? Now, once we defined what a block is and used all of the previous classes that we have created, now we can define the final GPT model, okay? And the input to this model, it's obviously going to be the size of our vocabulary. So the idea is to put as an input our vocabulary, to break it into those embeddings, which are one-dimensional vector for each token, then pass it through all the layers, and finally get the embedding values or the predictions for what the next token in our sequence should be. Now, once we have all of our classes defined, we can finally build our ChatGPT class. There, sequentially, we're going to run the different models we created so far and combine them together. Okay, so firstly, I'm going to explain to you what the GPT class involves, and after that, we're of course going to test it using this small configuration here. So let's go over it. Once we create our GPT class, the first thing that we want to add is the app configuration, so we can import the default number of layers, number of blocks, and so on. Now, if you remember, when we created our vocabulary, we created a mapping between tokens and numbers. So the idea was to represent the tokens with specific number. Okay, so for this reason, the input to our final model is going to be an embedding of a vocab size, and this is going to represent our vocabulary with embeddings. Okay, so here we're passing the number of embeddings, which means that now we're creating a 1D representational vector of each token with the embeddings, right? So for example, if we have 512 embeddings, each token of our vocabulary will be represented with a vector of 512 values. That way we can really capture how this token is important within a particular sentence, right? So once we create our embeddings, the next thing we need to add, and this also comes from the Attention is All You Need paper, is the positional encodings. Okay, so if you see here where we have our transformer architecture, you can see that once we create the embeddings, after that we need to sum them with the positional encodings of each of the tokens. Okay, and the positional encodings, they are pretty much matrices of block size by the number of embeddings, and they represent the importance of the position of a particular word within a sentence, actually of a particular token in our case. Then we defined our dropout class, and here in self.blocks we're actually creating multiple blocks. So what this means, if you remember, the block that we created here is a self-attention block, so we have annotation component, we have MLP component, and layer normalization. And this is pretty much this block that you can see right here in the gray. Okay, so if you see down here, we're having a multi-head attention, but also at the same time we can have multiple blocks of self-attention, and each of those blocks will separately analyze specific patterns into our vocabulary. Okay, so n layers is going to define how many self-attention blocks we're going to have. So for example, if we have 5 layers in our neural network, this means for each of those layers we're going to create a self-attention block, and an module list is simply creating a PyTorch list. And you might ask, but why don't we use just a standard list here? Well, PyTorch usually registers the neural network models only if they're in module list or sequential. Okay, so there's also a PyTorch function that is called nn dot sequential, okay, which is pretty much a quite similar thing. So that allows PyTorch to backpropagate through all of those blocks that we created within the list, and they will also be optimized during training. Okay, so then we have LayerNorm layer, and finally a linear layer defined here. Now the next thing that is interesting about this class, so the definitions I think are all clear by now because we had similar definitions in the rest of our classes, but here also we have this function that is called init weights. So that's done because usually the neural networks need a good starting point when they're getting trained. We can normally leave the default weights, biases, and standard deviations, but if we want to use specific ones that came out of some paper, for example, then we might want to specify them. And if we want to specify them, normally we use the init weights function, which we defined, of course, ourselves, and we can pass that to our neural network using the self.apply function. This will help us to have more stable training, as well as have a better starting point so we don't waste computational resources, since all the mappings and matrices are generated completely randomly, as well as the weights and the biases. So if we have some good starting point for those weights and biases, then our neural network will get trained more efficiently. So why we use the self.apply function and what does it do? The self.apply will recursively visit every neural network module that we have here, such as layers, blocks, embeddings, and so on. And for each submodule is going to have to call the init.weights. This will ensure that all the layers are initialized consequentially, and without this, for example, our linear or embedding layers are going to use the default PyTorch parameters, which might not match the best parameters for training the GPT model. Another thing that I want you to pay attention is our final linear layer, and you can notice here that we set the biases to false, which means that we want to remove the biases when we're estimating the parameters of the final layer. This is because the job of the head is to project the final hidden representation of each token into a vector of logits or very small numbers over the vocabulary. And once we do that, we're going to pass the result of the head through a softmax, and then we will find the final probabilities and the final values that will determine which is going to be the next token in our sequence. So then here in the forward, the idea here is to pass a specific token or sequence of tokens and then try to predict what is the next token in the sequence, right? So here, first of all, we will take the size of the index, and the size is going to be b by t, the batch and the time dimension. Then here I'm simply checking that the time dimension is more or equal to the block size, since we will have multiple blocks. And then here in the next line, we're creating the token embeddings for our tokens, right? So we'll create, for example, if we pass 2 tokens, we're going to create the embeddings for those tokens. Then here we're going to create our positional embeddings. We're going to sum them with the token embeddings, so just how it is done here in the paper. And then we're going to run the self.drop to have some of the parameters reinitialized to 0. And as I said before, this is specifically done so we don't overfit. Once we do that, for every block that we created, so you remember we created multiple blocks which are going to be pasted in this module list. So for every block in self.blocks, we are going to pass our tokens through each block, right? So once we do that, we'll pass through the LayerNorm, which we already explained. Then we'll get the final logits or the probabilities across all the vocabulary. What are the probabilities for us to have a specific token to come next, right? And once we do that, especially for training, we are going to compare the logits with the targets, right? So when we do that, we're going to get our loss, or what is the difference between what we expected and what the model actually produced, right? So remember, this is the forward function. So we pass through the model, and the forward function should allow us to train it. In order to train it, we need to pass the correct answers, and we need to estimate the predicted answers. And the predicted answers, or what is going to be the next element in our sequence, is going to be recorded in logits, and the expected answer is going to be passed in targets. And you will see how specifically this portion works when we cover the training of the model. Okay, but here, if we don't pass any targets, obviously we want to return the logits. But if we pass targets, we want to calculate the loss with a f dot cross entropy, and finally return the logits and the loss. Okay, and here we have another function which is going to help us to generate tokens once we have trained the model. Okay, so in the generate function, we're simply passing the current context or the current tokens that we want to pass to our model, the new tokens that we want to generate, and here we have a parameter called temperature. Temperature specifies how deterministic and how creative our model is. Okay, so we're gonna go through all the new tokens that we want to generate. So for example, if we pass the sentence to be, and then we expect to generate 3 more tokens, maybe we expected our model to generate or not to be, right? So we're going to loop over all the new tokens, and what we're going to do is, first of all, in the beginning of the function, you see that we specified no grad, which means that during that function, PyTorch will not compute gradients, because here we don't need to train the model, so respectively, we will not need to estimate the gradients for the backpropagation. And this line here is just specifying on what device we're going to run our code, whether we use CPU or GPU, but this is not important right now. And now here, this line, we need to have it because the GPT model can compute only within certain context length, right? So in our case, our context length is defined by the block size. So actually here in our example, the block size will be 8, which means that we can only see 8 tokens when we try to predict the next one. So what I'm doing here, I'm pretty much slicing our sequence and taking only the last tokens equal to the block size, okay? Then here we feed the current context into the model, so we run the forward function here, and we get the logits or the predictions for the next element, okay? Then from the logits, we take only the last token that was predicted, which should be the next token in our sequence, and we divided this by the temperature, as you can see here. As I said, this will specify whether our answer is more deterministic or more random. Then we estimate the final probabilities by running through the softmax function. Then we choose the next token. And finally, we add the newly generated token into our input sequence. So for example, if we want to get the next 3 tokens in our sequence, what we want to do is estimate the first token, append it to our sequence, then move 1 index up, then run again, and have the previously estimated token into our sequence. Okay, so this is what we're going to do here. Okay, so this is how our model should work, and now let's test it. So here I created an example configuration with vocabulary size only of 200 tokens. So from all the tokens that we had in our vocabulary size, we're going to take only 200. Block size, or what is going to be the window in which we're going to look at, this will be equal to 8. The number of embeddings for each token is going to be 16, and we're going to have only 2 blocks, or n layers will be equal to 2. Okay, so let me run this and let's analyze what we got printed. So here we created our start index to be 2b, right? And after that, once we have those letters, we want to see what is going to be generated after that as a text. So before feeding this to our network, we want to translate the words 2b into numbers. So then we can pass them to our model. And here you can see that 2b was passed through our tokenizer, and the tokenizer generated 3 tokens, 39, 58, and 46. Let's go back to our vocabulary and see if in fact 39, 58, and 146 are equal to 2b, right? So actually I'm going to search for 39, and you can see that in our vocabulary the token 39 is equal to the word or to the letter T. Okay, then the next one was 58, which is the letter O, and then the next one was 146, right? So let's go here. 146 is B, right? So this means our sequence, we correctly verified that our sequence of numbers in fact corresponds to the sentence to be. Okay, now after that we now enter to our forward function. Okay, and here inputs token indices, you can see that they're also exactly the same ones, so we successfully pass them to our network. And for those 3 tokens we generated 16 embeddings for each of the tokens. So 39 is going to be represented by this vector of numbers, 58 by this one, and then 146 by this one. Okay, so this is the representation. After that we'll create our positional embeddings and we initialize them to 0, but when we train the model, you will see that those are actually going to change their values depending on the position of the words. But for the first forward pass, they will be equal to 0. Then we are adding, just how it is displayed in the attention is all you need paper, we're adding the embeddings with the positional encodings, and we're getting an update to each and every embedding that is representing our 3 tokens, right? Now, once this is done, we are passing through the self-attention blocks. Okay, so after block 1 our vectors update, and after block 2 they update once again. So there we find some specific relationships between our tokens, and we're finding what is the relation between our tokens and what we have in the vocabulary. Then we pass through the final LayerNorm, as you can see here, so they get updated again. And finally we're passing through this head layer, the linear layer for the head, and you can see here that we're actually having for each token we're trying to predict what is the next token after it. Okay, so for each of our 3 tokens we're going to have 200 numbers, and each of those numbers is going to show us what is the probability of a specific vocabulary item to be next. So remember, the vocabulary that we passed was 200, right? So that's why here for each token we have 200 numbers related to it, and that will show what are the probabilities for each item or each token in our vocabulary to be next after this token. Okay, and those will be our logits. Now, once we exit the forward function, now we will start generating our tokens. Okay, so now we're gonna go through the generate function, and we will start predicting the rest of the tokens in the sequence. So remember, into our generate function here on this line we run self.index, which is going to again go through our forward function when we try to predict the next element in the sequence. So here we go again, we go through all of these operations of creating blocks, creating the logits. Okay, and once we create the logits we run through the softmax function right here. Okay, so we estimate all the logits, and once we run through the softmax function we find which token from our vocabulary is most likely to be next, and then we paste it right in our list. So we predicted that the next token is 21. Okay, so after the next iteration we're going to predict that the token after 21 is 8, and then it comes the final token, which is 181. Okay, so we predicted 3 tokens after the sentence to be. So once we generate all the numbers, now we want to decode them. So out will be equal to tokenizer.decode, and we're going to pass those numbers, and we'll find out that after 2b we have those tokens b, 0, and po. Of course those make absolutely no sense, but this is because our model is not trained yet. Currently all of our predictions are based on randomly generated matrices that need to be trained over multiple iterations. Okay, so this is what we're going to do next into our model training function. So this is where we actually train our model, and this function is pretty standard across most of the neural networks. What we do here is, first of all, we pass a model, which I will show how to create later on. So we do model.train, which will start calculating the gradients, and we set the initial loss equal to 0. Then for every block in our, or actually every batch in our data loader, we're going to run one step. So firstly, we're going to take from our data X, which, if you remember, is simply a matrix with sequences of tokens, and then in Y are going to be our predictions that we know. So in X we have the questions, and in Y we have the answers, or what is the next token that should be in the sequence. Then we run the model for X and Y, which will activate the forward function here, but now we're going to pass indexes, which is going to be X, and targets, which is going to be Y. Then once we estimate the matrix for X and Y, we're going to compare those right here. Then we're going to reset the gradient and run the backpropagation, which is going to go through all of our layers, and based on the rate of change of what comes after the neuron is going to update the specific weights and biases at that neuron, and this will happen across all the matrices. This is what the backpropagation is going to do. So once we run the backpropagation, then we're going to be able, based on the loss, or what's the difference between our initial estimation and what's the true value of what comes next, we're going to be able to update those weights and biases. Then this line here is going to prevent our gradient from exploding or getting too large. And to do that, you can use torch.nn.utils climp grade norm. And here we pass the model parameters and the max gradient norm, which is the maximum one, which is going to be in our case 1, as you can see here. Then we do optimizer.step to move one step further. Then here we're going to add some log for the total loss. And then here I added a print statement that will show for every iteration and every step how much was the loss. So that way we'll make sure that the loss is decreasing. So our goal always is for the loss to always be decreasing, which means that our predictions are more close to the actual values, right? Then here I added a simple function that will allow us to chat with the model once we train it. And it's a very simple function. I'm not going to go too much into it, but what I simply do is I take a user input here. You can of course choose to exit or quit the chat. Then I'm going to keep some track of the history. So what the user said before is going to be important. And then when the user types something, it's going to be recorded in the history. Then we're going to encode it into token numbers. And then I'm going to use the generate function, which will come from the GPT class, and I'll specify how many new tokens I want to generate, and also I'll specify what the current history is. Okay, so the max tokens is currently set by default to 200. Finally, once I get the output or the predicted tokens, I'm simply going to decode them, and I'm going to put them in a nice way so we can see AI is saying something. So the idea is to get exactly the same experience as if you would text with ChatGPT. And remember, this is completely our model. We're not calling an API or reaching to any other external server. This is a model that we train on specific data, and after that we're interacting with that model. So that's important. Now that we have all of our functions and classes created, then here we can actually start our project. Okay, so here you can see I'm actually calling this file that we have into our folder, which is going to be the file with all the text information. So this is the file that will train the model right now. So I can train actually everything very fast. This file has just a few sentences, so our model obviously will not be very sophisticated. Okay, then I will create our tokenizer with a vocab size of 1000 tokens. Then here I'm simply going to print our vocabulary, so you will be able again to see the mappings between tokens and numbers assigned to those tokens. Then I will set here the block size equal to 64. So in this example run, I will have 4 layers. So 4 self-attention blocks, 4 self-attention heads. Each token will be represented by 256 embeddings. Dropout would be 10% of our predictions, and I'm going to use GPU if it is available. So once the configuration is all set, then I will create the model. And once we have that, I will create a dataset just in the same way as we practiced. So here will be the dataset, which will be one-dimensional array of the complete text file represented in tokens. Then we're going to break that with a data loader, and we're going to break it into separate batches with batch size of 16 tokens. After that, we're going to set our optimizer. We're going to choose Adam, which is one of the most popular optimizers. And then here we're going to start training our model. So the number of training sessions or epochs that we're going to do is going to be 3. And for each epoch, we're going to run our train function, which we defined right here. And then I added this line here so we can actually evaluate the model. So after each epoch, we are going to print something after the 2b, right? So after each iteration, I will generate 200 tokens after the token 2b, and that way we will see how our model improves. In the beginning, obviously the text is going to make no sense, but you will see that with every iteration, it is going to make more and more sense to us. So you can see that's why here I run the generate function and I generate 200 tokens after the initial start tokens here. Okay, and finally I added those lines. You don't need to do it, but I added them just so you can actually save the model. So once the model is trained, you can actually save it using this. So I'm going to create a new directory called checkpoints, and inside I'm going to save the weights from every epoch. Okay, so once that's done, we're going to run the chat function, so we'll be able to chat with our model. Okay, so I run the main function. Okay, and actually nothing happened here because I will also need to call that function. So I will just need to copy, paste right here and run it. Okay, so you can see here our vocabulary was created of 1000 tokens, and you can see that here our prompt completely exploded. So I'm going to stop it for a second, and this is because I will need to remove all the logging that I added into our GPT class. Okay, so I'm going to remove those prints here because we no longer need to print all the matrices, right? So I'm going to remove those. Okay, let's save that. All right, and let's run the main function again. Okay, so now you can see here, guys, firstly we printed the vocabulary, and then in the epoch 1 we run 180 steps, and you can see that our loss initially was 6.3 and it went down to 2.1, and as we moved forward it then became 0.45 and then 0.17. So you can see that firstly here the text doesn't make much sense, but now here after the second epoch you can see the first published in 19-ish by and so on. He plays 69 games. Now here we started our chat after that, and you can see that really the words make some sense. Also bear in mind that some of the words, they are broken down into different tokens. For example, this one, university, even though the word was generated by 1, 2, 3, 4 tokens, our AI model was capable of correctly pasting them one after another, as you can see here. So we can say that our model definitely improves. Now here, for example, when we chat, we can see here that the group appears to have created their own group after splitting, right? So now you can see that after just 3 epochs, our model really starts making a lot of sense. Now, obviously, if you want to create a large reasonable model, you need way more than this. So I'll need to pass the complete wiki set and also increase the number of embeddings, the number of layers and heads, which will take considerably more time to train. However, this will definitely improve the results and will allow the model to actually create meaningful answers. But here we have it, guys. So this is the complete GPT model. Please feel free to check out the notebook and train it on even higher ranges of datasets and vocabulary. Bear in mind that here we used only 1000 tokens vocabulary, but the original ChatGPT has a vocabulary of over 50,000 tokens. So there is definitely spaces for improvement, but this model is definitely scalable and you can train it on any data. So that's it. Thank you very much for watching. Please make sure that you subscribe my channel and give thumbs up to this video. Soon I'm also going to create very detailed videos on AI agents as I'm building a few. Thanks for watching, and I will see you in the next video.